Today we will talk about generations of electronic computers, including fifth generation of electronic computers. Before the advent of modern computers. The principle of the modern computer was first described by computer scientist Alan Turing, who set out the idea in his seminal 1936 paper, on computable numbers. Turing reformulated Kurt Gödel's 1931 results on the limits of proof and computation, replacing Gödel's universal arithmetic-based formal language with the formal and simple hypothetical devices that became known as Turing machines. He proved that some such machine would be capable of performing any conceivable mathematical computation if it were representable as an algorithm. As part of 12th century wave of Arabic science flowing into Europe via translations, these texts proved to be revolutionary in Europe. Al-Khwarizmi's Latinized name, algorithmus, turned into the name of method used for computations, and survives in the modern term algorithm. It gradually replaced the previous abacus-based methods used in Europe. Al-Khwarizmi's influence didn't stop at algebra. His work extended into the realm of algorithms. His name itself gave birth to the term algorithm, with algorithmi being the Latinized version. He developed systematic methods for solving mathematical problems, laying the groundwork for algorithmic thinking that would become the cornerstone of computer science. The golden principle of Al-Khwarizmi. The Al-Khwarizmi principle states that all complex problems of science must be and can be solved by means of the following 5 simple steps. 1. Break down each problem into a number of elemental or atomic steps. An elemental or atomic step is one, which cannot be simplified any further. 2. Arrange all the elements or steps of the problem in an order or sequence, such that each element can be taken up and solved one at a time, without affecting other parts of the problem. 3. Next, find a way to solve each of the elements separately. Because each element has been simplified to the maximum, it is very likely that the solution of an elemental step will itself be extremely simple or elemental, making it available with relative ease. 4. Then proceed to solve each element of the problem, either one at a time or several at a time, but in the correct order. 5. Thus, when all steps are solved, the original problem itself has also been solved. Generations of electronic computers: first generation, vacuum tubes; second generation, transistors; third generation, integrated circuits; fourth generation, microprocessors; fifth generation, artificial intelligence, quantum computing, graphene, photonic chips, etc. First generation of electronic computers: vacuum tubes. The invention of vacuum tube in 1906 opened the gates for the development of electronic computers. Vacuum tubes were used as electronic switches instead of relays in earlier electronic computers. Vacuum tubes were noiseless and could work at a fantastic speed as compared to relays. Colossus was the world's first electronic digital programmable computer. It used a large number of valves, vacuum tubes. It had paper tape input and was capable of being configured to perform a variety of Boolean logical operations on its data, but it was not during complete data input. To Colossus was by photoelectric reading of a paper tape transcription of the enciphered intercepted message. The reading mechanism ran at 5,000 characters per second, with the paper tape moving at 40 feet per second. Colossus decrypted the vast quantity of enciphered high-level telegraphic messages between the German High Command and their army commands throughout Europe. Details of their existence, design, and use were kept secret well into the 1970s. Winston Churchill personally issued an order for their destruction into pieces, to keep secret that the British were capable of cracking Lorentz SZ ciphers, from German rotor stream cipher machines. During the oncoming Cold War, 2 of the machines were transferred to the newly formed GCHQ and the others were destroyed. As a result, the machines were not included in many histories of computing. In 1943, Electronic Numerical Integrator and Calculator, ENIAC, was built at University of Pennsylvania. It could perform 5,000 additions and hundreds of multiplications per second. ENIAC's development and construction lasted from 1943 to full operation at the end of 1945. The machine was huge, weighing 30 tons, using 200 kilowatts of electric power and contained over 18,000 vacuum tubes, 1,500 relays, and hundreds of thousands of resistors, capacitors, and inductors. One of its major engineering feats was to minimize the effects of tube burnout, which was a common problem in machine reliability at that time. The machine was in almost constant use for the next 10 years. The ENIAC, Electronic Numerical Integrator and Computer, was the first electronic programmable computer. Although the ENIAC was similar to the Colossus, it was much faster and more flexible. It was unambiguously a Turing-complete device and could compute any problem that would fit into its memory. Like the Colossus, a program on the ENIAC was defined by the states of its patch cables and switches, a far cry from the stored program electronic machines that came later. Once a program was written, it had to be mechanically set into the machine with manual resetting of plugs and switches. The first computer that used stored program concept was the Electronic Delayed Storage Automatic Computer, EDSAC, developed in 1949. Another was Electronic Discrete Variable Automatic Computer, EDVAC, that used the same concept. The program and data were fed in the EDVAC through punched paper tapes. The first commercially successful machine was Universal Automatic Computer, UNIVAC-I. It was made operational in 1951. It was a self-checking computer and could work 24 hours a day. UNIVAC-I used magnetic tape as input media. The shortcomings of first-generation computers were: 1. Very big in size, 2. Slow in speed, 3. Low reliability, 4. Large power consumption, 5. Difficult maintenance. Before we move forward, we ask you to subscribe Insight Edge 360 YouTube channel. Second generation of electronic computers, transistors. The bipolar transistor was invented in 1947. From 1955 onward, transistors replaced vacuum tubes in computer designs, giving rise to the second generation of computers. Compared to vacuum tubes, transistors have many advantages. They are smaller and require less power than vacuum tubes, so give off less heat. Silicon junction transistors were much more reliable than vacuum tubes and had longer service life. Transistorized computers could contain tens of thousands of binary logic circuits in a relatively compact space. Transistors greatly reduced computers' size, initial cost, and operating cost. Typically, second-generation computers were composed of large numbers of printed circuit boards such as the IBM Standard Modular System, each carrying 1 to 4 logic gates or flip-flops. Transistorized electronics improved not only the CPU, central processing unit, but also the peripheral devices. The second-generation disk data storage units were able to store tens of millions of letters and digits. Next to the fixed disk storage units, connected to the CPU via high-speed data transmission, were removable disk data storage units. The early 1960s saw the advent of supercomputing. The Atlas was a joint development between the University of Manchester, Ferranti, and Plessey, and was first installed at Manchester University and officially commissioned in 1962 as one of the world's first supercomputers, considered to be the most powerful computer in the world at that time. Atlas also pioneered the Atlas Supervisor, considered by many to be the first recognizable modern operating system. A series of computers at Control Data Corporation, CDC, were designed by Seymour Cray to use innovative designs and parallelism to achieve superior computational peak performance. The CDC 6600 outperformed its predecessor, the IBM 7030 Stretch, by about a factor of 3, with performance of about 1 megaflops. The CDC 6600 was the world's fastest computer from 1964 to 1969, when it relinquished that status to its successor, the CDC 7600. Third generation of electronic computers, integrated circuits. In the 60s, the integrated circuits, ICs, appeared with the development of microelectronics technology. An IC chip contains many components, such as transistors, diodes, and resistances, interconnected with each other. The third generation of digital electronic computers used integrated circuit chips as the basis of their logic. The idea of an integrated circuit was conceived by a radar scientist working for the Royal Radar Establishment of the Ministry of Defense, Geoffrey W. A. Dummer. In 1958, Jack Kilby invented the hybrid integrated circuit, hybrid IC, which had external wire connections, making it difficult to mass-produce. In 1959, Robert Noyce at Fairchild Semiconductor invented the monolithic integrated circuit chip. It was made of silicon, whereas Kilby's chip was made of germanium. The basis for Robert Noyce's monolithic IC was Fairchild's planar process, which allowed integrated circuits to be laid out using the same principles as those of printed circuits. The planar process was developed by Noyce's colleague Jean Hoerni in early 1959. Based on Egyptian Muslims' work on semiconductor surface passivation by silicon dioxide at Bell Labs in the late 1950s. In 1960s, following this research, Mohamed Atalla and Dawon Kahng demonstrated a device that had the structure of a modern MOS transistor. Kahng pointed out several advantages of the device, notably ease of fabrication and its application in integrated circuits. Nearly all modern IC chips are metal oxide semiconductor, MOS, integrated circuits, built from MOSFETs, metal oxide silicon field effect transistors. The MOSFET, also known as the MOS transistor, which was invented by Mohamed Atalla and Dawon Kahng at Bell Labs in 1959, made it possible to build high-density integrated circuits. In contrast to bipolar transistors, which required a number of steps for the p-n junction isolation of transistors on a chip, MOSFETs required no such steps but could be easily isolated from each other. Its advantage for integrated circuits was pointed out by Dawon Kahng in 1961. The list of IEEE milestones includes the first integrated circuit by Kilby in 1958, Hoerni's planar process and Noyce's planar IC in 1959, and the MOSFET, MOS transistor, by Mohamed Atalla and Kahng in 1959. Third generation, integrated circuit, computers first appeared in the early 1960s in computers developed for government purposes, and then in commercial computers beginning in the mid-1960s. The first silicon IC computer was the Apollo Guidance Computer or AGC. Although not the most powerful computer of its time, the extreme constraints on size, mass, and power of the Apollo spacecraft required the AGC to be much smaller and denser than any prior computer, weighing in at only 70 pounds. 32 kilograms. Each lunar landing mission carried 2 AGCs, one each in the command and lunar ascent modules. Some of their early uses were in embedded systems, notably used by NASA for the Apollo Guidance Computer, by the military in the LGM-30 Minuteman Intercontinental Ballistic Missile, the Honeywell Alert Airborne Computer, and in the Central Air Data Computer used for flight control in the U.S. Navy's F-14A Tomcat fighter jet. Digital Equipment Corporation became the number 2 computer company behind IBM with their popular PDP and VAX computer systems. Smaller, affordable hardware also brought about the development of important new operating systems such as Unix. Fourth generation of electronic computers, microprocessors. Very large-scale integrated circuits, VLSI, were developed in 1971. A VLSI contained a complete central processing unit, CPU, on a single silicon chip. On November 15, 1971, Intel released the world's first single-chip microprocessor, the 4004, on a single MOS LSI chip. The first microprocessor Intel 4004 was a 4-bit processor capable of performing arithmetical, logical and control functions. Intel developed an 8-bit microprocessor in 1973. Later on, many other companies also started producing microprocessor chips like ZX80, ZX81 etc. The use of microprocessors produced cheap computers called microcomputers or personal computers, PC. These computers used an 8-bit processor and results could be displayed on TV sets. Another popular series of personal computers was Apple series, designed in 1976 using 8-bit microprocessors. Commodore PET were also the popular personal computers. In 1978, the evolution of 16-bit microprocessors greatly increased the processing speed of the computers.